We will now look at plane waves in lossy material. And what we mean by that is that the material has some conductivity, so there can be current flow. So as the wave propagates, I squared R losses will attenuate the energy in the electromagnetic wave. Your textbook begins the treatment of electromagnetic waves with looking at waves in lossy material, and then treats propagation in lossless materials as a special case. Here we have Maxwell's equations in point form. So if we have conductivity for the current density, we're going to replace it with the conductivity times the electric field intensity. Even though the material is conducting, the charge density is going to still be zero. This is a condition that bothered me for a while and took me a while to figure it out, why the charge density can be zero when the material is conducting. Here is a representation of our conducting material. The minus signs are the conduction electrons, and the positive signs are the net charge of the nuclei and the bound non-conducting electrons. So our electromagnetic wave is going to propagate in the z direction, and the electric field intensity is going to be in the x direction. Since there's only an electric field intensity in the x direction, the electrons are going to move up and down as the wave is propagating. If you focus on some region like this, the net charge in this region is going to be zero because the sum of the negative and positive charges in this region will sum to zero. As the wave propagates through, the net charge in any region will remain zero because the electrons leaving that region are compensated by electrons entering that region. And that's why we can set the charge density equal to zero. With these two relationships, I can rewrite our Maxwell's equations just in terms of the electric and magnetic field intensities. With these substitutions, I rewrite Maxwell's equations here, plus let me replace the electric and magnetic field intensities with their phasor forms. To take a time derivative when you're working with phasors, you just multiply by j omega. So here and here we will multiply by j omega, and our first two equations become these two equations. Let's take the curl of both sides of this equation, which will give us this equation right here, and then we're going to substitute for the curl of h this term right here. Using this vector identity and the fact that the divergence of the electric field is zero, we can rewrite the left-hand side of this equation as minus the Laplacian of the electric field intensity. We are going to call this term here gamma squared. Taking the square root gives us gamma, and gamma is going to be a complex number. We'll call the real part alpha and the imaginary part beta. Gamma is the propagation constant, alpha is the attenuation constant, and beta is the wave number. Beta will play the same role it did for our wave propagation in lossless material, and we'll see that alpha describes the attenuation of the wave as it propagates. Rewriting this term as gamma squared, we can write our wave equation as the Laplacian of the electric field intensity minus gamma squared times the electric field intensity is equal to zero. By direct substitution, you can show that this is a solution to our wave equation. This solution will play the role that our plane wave did in the lossless case. Let's rewrite gamma as alpha plus j beta in our solution, and then multiply by e to the j omega t and take the real part. So here we have the solution to our Maxwell's equations in lossy material, and we see it looks very much like the solution we had in the lossless case, except for this additional term which describes the attenuation of the wave as it propagates. The velocity with which the wave is moving is still omega over beta, and beta is still our wave number. Let's find the corresponding magnetic field intensity. So here we have Faraday's law. So let's take the curl of our solution, which only has one component, the x component. And we find our corresponding form for the phasor representation of our magnetic field intensity. We can find our intrinsic impedance by taking the ratio of the electric field intensity to the magnetic field intensity. And we find that our intrinsic impedance is now going to be a complex number. Rewriting the amplitude of our magnetic field intensity as the ratio of the amplitude of the electric field intensity to the intrinsic impedance, we see that we're going to have a phase shift between the electric and magnetic fields when there's propagation in a lossy material. Multiplying by e to the j omega t and taking the real part, we have the final forms for our magnetic and electric field intensities for propagation in the lossy material, with this being the intrinsic impedance. At this point, your textbook introduces the special case of propagation in a lossless material. In a lossless material, sigma will equal 0, so you have no current flowing, no I squared R losses. If we set sigma equal to 0 in the equation for our propagation constant, gamma, we find that gamma only has an imaginary part whose value is omega square root of mu epsilon. So beta is equal to omega square root of mu epsilon, which is the condition we obtained previously when we were treating just the lossless case. So the velocity of our wave is 1 over the square root of mu epsilon. Going to our intrinsic impedance equation and setting gamma to 0, we find our intrinsic impedance is a real number, and we obtain the same value we had when we were dealing with the lossless case, square root of mu over epsilon. Setting sigma equal to 0, these results for propagation in lossy material reduce to the results we obtained previously when we were treating lossless material.